Thank you very much. So, have you recently dealt with water shortages or with, I don't know, heavy rain precipitations? Well, this problem may be due to climate change, which is an important issue that we all know that we need to address, right? So that's why me, Sánchez Miranda, and my partners Erick Hernández Silva and Ignacio, Ferro, Salinas, and Miguel Gonzalez-Mendoza have done an investigation on predicting precipitation using machine learning models. So if we could go to the next slide, please. So this is the agenda. These are the topics that we are going to discuss in our presentation, and we will start. We first are going to make an introduction, talking a little bit about the problem and why we think it is important. So, as we all know, climate change alters a lot of patterns, of forecasting patterns, from temperatures to precipitation, and this is due to extreme weather events like droughts or tornadoes, hurricanes, and all that kind of stuff. And that makes traditional methods have a hard time predicting precipitation and these patterns that are altered. That's why we think that applying machine learning is important, because with this we may be able to adapt to these changes. We wanted to focus especially on Mexico's metropolitan area, because it is a region that we think it's very vulnerable to all this kind of stuff because of its dense population and economic activities. So we also want to talk a little bit about the related work we have studied for these kind of problems. We first have a study in Hungary. This study in Hungary uses regression analysis that correlates the topographical data with the precipitation, like latitude, longitude, and also slope, elevation, and all this kind of data, and it correlates it to precipitation, and it has had very good results. We have another study in China that uses kriging. Kriging is a geostatistical spatial method that it's also very well used for applications like predicting unknown climate variables based on spatial data. And this study uses kriging along with other regression techniques, and it uses historical data to predict this. Finally, we have another study in Turkey that uses polynomial regression. They even did the Polbrek software, that is a software that is also used for predicting extreme precipitation in many regions. It uses also historical data from 66 weather stations, and it also has very good results. And what we saw in common with these three studies done in the international overview is that they use historical data to predict the precipitation, so that's where we wanted to focus. Now, on the national overview, we really don't have studies in Mexico here that predict precipitation, but we have a study by Olvera Fuentes that uses fuzzy cognitive maps to simulate what will happen in Mexico's metropolitan area if we reduce precipitation or if we increase precipitation. So this gave us valuable insight, making the conclusion that precipitation is very important in this area, and it's greatly correlated with the climate change. We also have another study made by System. This is concentrated in Monterrey's metropolitan area, which is another area that is widely densely populated and very economical active. So they predicted, this study, I think it was in 2016, and they predicted a water crisis, which is what has happened in recent years. And they also concluded that it was greatly related to precipitation and to climate change. And now we're going to talk a little bit about the experimentation and the results we had.
Okay, thank you. So, first of all, I'd like to talk a little bit about the data set that we used for this research. We found a source that is called the Global Water Monitor, and it's an interesting source because it's a consortium of multiple private organizations and also universities from all over the world, from places like the United States, Australia, and others. And it's an interesting tool because it gathers satellite observations across the globe from more than 60 years in the past. So it's kind of useful for this research, and it's also promoted by the World Bank. So we decided to go this way. Some variables that we found with this tool were the precipitation, the temperature, the soil water level, the surface water level, and underground water. You may be wondering why the last variables have no unit in them. This is because these variables measure the proportion of water in each particular ground level. So that's how the data set gives us these variables. And also, so to use these variables, we go into the methodology, which we divided into two main parts. The first one, which is the data cleaning, integration, and formatting, and the second, which is the modeling and validation and visualization of the results. Some noteworthy parts of the methodology or on the preprocessing of the data are that we followed a normalization with min-max scaling, and this was an important step because, as you can see, the variables, for example, precipitation and temperature, they have different scales. So we use the min-max scaling to avoid an unbalanced contribution of the features on the results. Then after that, for handling the missing values, we also encountered missing values, but these were different from variable to variable. For example, in the precipitation variable, we only had 2 missing values, which is a small fraction of the entire data set, which was a total of 500 observations. So for this variable, we decided to do an average of the surrounding years where the missing variable was encountered. And this is because the precipitation is a seasonal phenomenon, and the amount of missing values were very few. So for the other missing values in the other variables, we decided to go with a more traditional strategy for imputation, which was linear regression. And finally, we had one variable where the missing values were too many. The variable of underground water, this variable had more than half of the values missing, as this is well, we decided to drop this variable entirely, because if we had kept this variable, we would have been working with more fictional values than real values, and that could have introduced some bias into the model. So we decided to do that strategies for handling the missing values, and then we performed a split of 70% for the training data and 30% for the test data to train the models, which is the next part of the methodology.
Okay, so as my partner Luis mentioned, after doing this preprocessing pipeline, we then decided to get the metrics that we were going to use. So as basically our modeling was about predicting the amount of water in millimeters that would fall from the sky by rain. We decided to use mean squared error, the mean absolute squared error, the root mean squared error, and R squared, coefficient of determination, and the MAP, the mean absolute percentage error. Basically, as you may know, the errors, as the lower they are, the better they are, because it means that our predictions are more accurate. And the coefficient of determination basically tells us how our model fits the data, right? So the higher the better. So now talking about our models, we basically use 3 types of models. The first one is linear regression. The reason of this is because when we plotted all the data points, we saw basically that it had kind of a linear behavior, not the best. As you may see in the results, it is not the best model, but it was enough to try this modeling, right? Then we have the random forest. Basically, we chose the random forest because it is better at handling non-linearity, and well, it might be the opposite of linear regression, right? It's better non-linearity in this case, and as you may see, it has better metrics than the linear regression because of that. And then we have the super vector machine, which has like a similar performance as the random forest. Basically, we choose this model because it is good at handling complex patterns, right, in the data. And well, it is important to note that, as you may see in the random forest and the super vector machine, we also tune them by using a random search method. And just to make sure that these models are good enough, we performed some cross-validation, right? So the results you are seeing in there maybe have lower values or worse values, right, than the other ones that we made because of the cross-validation, right? But they are still being good values. And then we have an ensemble model, which is quite easy. It basically takes the output of each of the other models, and we get the mean from that, and that will be basically our output, right? Why did we do this instead of like a multimodal model? Because we have like 3 different kind of models, each one with some strengths and weaknesses. But for example, the linear regression, which is good at linearity, but our data is not completely linear, right? So we have the random forest, which is good with that, handling non-linearity, and the supervector machine handling this complex data, right? So each other strength has the strengths of the other's weaknesses, right? Well, so after doing all these models, we also generated some clustering. Basically, we cluster each of our variables against the other, as you may see there, soil water against surface water, against temperature, and against itself. That doesn't count, of course. And after doing this clustering, we basically took all these data points and got the mean precipitation from them, so we could know, well, that basically the mean precipitation of each cluster. And we got that, as you may see, the cluster number 0, which is the one that has the lowest precipitation, and cluster number 1 is the one with the highest one, and cluster number 2, the one with the moderate. Why is this important? Because we can get all the characteristics, soil water, surface water that is in each group, and we can correlate the data, well, the output of the ensemble model of the previous models also with this clustering, right? So if we get an output from the previous model, like, I don't know, 0.5 millimeters, then we can get into the clustering algorithms. Well, I forgot to mention it, but we use K-means clustering algorithm with K equals 3. But we can come here, put the data in here, the input data, and see which cluster the characteristics go into, right? And then we can correlate that if our output was 0.5 and the data is in cluster number 1, okay, we have like a double confirmation, right, from this.
So now we're going to discuss a little bit about the results. Next slide, please. So as my teammates have shown the methodology, we can see that applying these models and the clustering, we can have very good results and valuable insight about what are the variables and how they affect the precipitation. We also saw that the information we obtained with the clustering and with our models was consistent. And as we can see in this plot over here, we have the actual values of precipitation in Mexico City and the predicted models by our ensemble model. We can see that it's mostly accurate. It deviates in some points, but it remains consistent. So that we also want to highlight that this is tailored for different regions, not just Mexico City. We also have predictions for Mexico State and for Morelos. So each variable performed differently and affected differently the precipitation, and all this information is also available in the with the clustering, and that's how also we saw how these variables affect precipitation.
Okay, so to conclude our presentation, I would like to make some remarks. First of all, is that water shortages in Mexico are a relevant topic now more than ever. So these types of research where environmental factors can be built and it can be gathered by the relevant authorities to make decisions about the future of the management of water in Mexico. Also, we saw that clustering and with the prediction analysis, we could model and identify environmental factors in multiple regions, not only in Mexico City, but also in Morelos and in the state of Mexico. And this also could be leveraged, seeing that these different regions may have different demands of water and supply of water. So the authorities could use this information to make relevant decisions. And also we saw with the metrics that we exposed that the ensemble model outperformed the individual models by themselves. And this proved to be a valuable machine learning strategy in this research. But there's still room for improvement, so that's why we outlined some steps that could be followed for future work. For example, to refine the existing models, and also to consider more modern models and more techniques for handling the missing values to see which combination is the most suitable and yields the most convenient results for this task. And with that, we'd like to thank you all for your time and your attention, and that's it. Thank you.
With the cross-validation results, what do you think by using cross-validations affected the results?
Well, I thought about this a little bit, that using the cross-validation with random search for hyperparameter tuning, what it did was basically to make the models more consistent and reliable on the training split of the data set, but that does not necessarily mean that it will perform better in the test set. I was a little bit shocked that the results with cross-validation and random search had a little worse performance, but yeah, that's the justification that we made it. Maybe with other strategies for tuning or with more time for tuning, we would have found better models, but that could also be studied for future research.
Thank you. Any other question? Pueden preguntar en español. Bueno, ya que estás, now that you're in this slide, I'm wondering if can you give us an idea or how good or bad is the best result you have, for instance, the ensemble? I mean, I don't know, you can compare all of these models to each other, but with respect of a reference or, I don't know, expected precipitation, what can you tell us about?
Yeah, well, since we did perform a little bit of a state-of-the-art comparison in the article, but right now we did not have the necessary information to compare these results to those, but in the article there's a little bit more information about that.
Yes, basically because as you may have seen in the previous slides, there are no too much state-of-the-art here studies like this in Mexico.
How the government does, this is a question for all three papers, how the government measures this, because I guess they have an approach to measure this, right? So are you aware of how they estimate the precipitation?
So precipitation, we use data from the Global Water Monitor, which is an international organization, but most organizations do this by measuring the millimeters, the precipitation, the average millimeters of water that la lluvia que cayó.
Okay, but they do not predict ahead.
Sorry?
They do not make predictions ahead, like.
They use techniques like the ones I mentioned before, like kriging, which uses, it's not entirely machine learning, but it uses spatial data, like the data we have, like soil water, underground water, temperature, all this kind of data, and they introduce it to kriging, which uses this spatial data and for example, latitude, longitude, this information, and with that, they are able to predict the precipitation.
Thank you. So, if we don't have any further questions, please, we have a question.
You mentioned that for some missing values, you use an approach where you average the values of the other instances that were more closely regarding time, years. Is that correct? So would it be possible to exploit temporal relationships between data instances to maybe improve the prediction of your models using other models that take advantage of that sort of relations?
Yes, thank you very much for the question. I agree. I think that question is very, has a very good idea, because some of the state-of-the-art models that deal with time series, and one that was mentioned in the presentation before was the long short-term memory, for example. These kinds of models are more well-suited for time series prediction, and maybe this is also a step that could be valuable in the future work. But for us, we decided to make this as a starting point of the more traditional models that have been used in machine learning. But definitely would be worth it to go with exploring all those models that are suited for time series. Thank you very much.
Well, thank you. Let's thank Carlos again. Thank you so much for your talk.